two types of compounds. What were the two types of compounds we talked about last week?
Ionic and molecular.
Ionic and molecular. And so we said that the big difference, probably tell them apart, are ionic compounds have a metal in them, right? The bonding that holds them together is also very different. Ionic compounds have ionic bonds, and molecular compounds have covalent bonds. I wish they would have called them covalent compounds to make it even easier, but molecular compounds have covalent bonds. So in the video, we briefly talked about the difference between them. And so like chemistry cat and, I don't know, we'll call him science dog. I don't know if he has a name. In ionic compound, electrons are given and taken. So in an ionic bond, the ions, remember we have positive and negative ions, the positive and negative attract each other and hold them together. We talked about ions that like to gain electrons, we talked about ions that like to lose electrons. Those happen at the same time. An ion doesn't just give away an electron and it flies away, then another one picks one up. Electrons don't just fly around. When one ion or atom gives away an electron, it's giving it directly to another atom that's gaining an electron. Molecular compounds share electrons. Okay? So in the ionic compound, an electron gets transferred. One or more electrons gets completely transferred from one atom to another, which makes a positive ion and a negative ion, and then that holds the two atoms together. That's always going to be between a metal and a non-metal. Okay? In order to have that ionic charge, you're going to have a metal around. Ionic bonds are really, really strong. Covalent bonds, though, share electrons. These are between nonmetals, and so what essentially happens, and we'll see this, is you have two atoms that are very close to having their 8 valence electrons that they want to have. And so they decide, well, if I share an electron with the electron next to me, and they share one with me, we'll both get our 8. Because if two atoms are sharing an electron, they're both going to count it as being theirs. And so in the ionic bond, the electron gets transferred, and so the positive and negative forces hold them together. But in the covalent bond, essentially you have two atoms each holding on to the same electron, and because neither one wants to let go, the two atoms are bound to each other. This was video. In a covalent bond, though, there's not necessarily completely equal sharing. There are polar covalent bonds, and then there are non-polar covalent bonds. And imagine if I hold this out to her, and the electron is directly in between us. It's evenly between us. We're both equally sharing that electron, and so that is a non-polar covalent bond. But if she pulls it harder than I do, so the electron is closer to her, she's going to have more of that electron. And that electron is negatively charged, so she is going to have a partial negative. If I hold it stronger, I get more electron, so I am more negative. That is a polar covalent bond. Essentially, if you have two atoms of the same element bound together in a covalent bond, it's going to be nonpolar. If you have two different elements bound together, it's going to be polar. And that's because every element has a different strength that it pulls on that electron. And that was called electronegativity. So electronegativity is how strong something is going to pull on that electron. So every element has different electronegativity, which means if you have two different elements both pulling on the same electron, one has to be stronger than the other. If you have two of the same element, they both have the same strength, and so it's non-polar covalent. The only exception is carbon and hydrogen. They're two different elements, but carbon and hydrogen form non-polar covalent bonds. Okay. This was the last slide of the video. If you're looking for ionic versus covalent bonds, just look, is there a metal? Just like we did with ionic compounds, if there's an ionic bond, there has to be a metal. And if there's a metal, there cannot be covalent bonds. So again, the metal is your key. So we said last week that in ionic bonding, the metals were the ones that lose electrons, and the nonmetals gain electrons. We talked about how whether they want to gain or lose depends on the electron configuration that they're starting with. They want to be a noble gas, and so they will lose or gain electrons in order to get the nearest noble gas. So this is the formation of sodium chloride. This is the reaction between sodium and chlorine to make sodium chloride. And so sodium is our metal, chlorine is our nonmetal, and so electrons are going to literally be transferred from the sodium metal to the chlorine gas. When the electrons get transferred, the sodium becomes positive, chlorine becomes negative, and so now we have a combination of sodium chloride held together by all those positive and negative charges. Because we have positive and negative charges, and remember we talked about the crystal lattice where they get this neat arrangement. Imagine in our sodium chloride, we have the atoms arranged like this. The green ones are our chlorines. They're negatively charged. The yellow ones are our sodiums. They're positively charged. Yes, we have the yellow and the green attracting each other, but we also have two yellows next to each other. Two positives repel each other. Two negatives repel each other. So what you have is this chunk of salt with all of these forces going on at the same time. All the chlorines are repelling each other, all the sodiums are repelling each other, but the sodiums and chlorines are attracting each other. And so the atoms move around until they find the spot where all the forces balance out. And that's what causes this alternating pattern. In this pattern, the repelling forces and the attractive forces all cancel each other out, they balance each other out, and atoms just sit in one place. In a covalent bond, the electrons are being shared. So we don't have that positive and negative in terms of the entire atom, but we do have positive and negatives in terms of the subatomic particles. So we have two atoms here, and the two lobes shown here, and in the center of each, we have a nucleus. And remember, the nucleus has protons and neutrons. Neutrons have no charge, though. And so the nucleus is positively charged. The electrons are flying around on the outside. They're negatively charged. And so we have attraction between the electrons in the nuclei. So this one electron is being shared by both. It has attraction to both nuclei. But the nuclei also have positive charges, and so they repel each other. The electrons also repel each other. So again, they move around until they find their happy place, where all the forces balance, and they will stay just like that. So carbon dioxide is an example of a molecular compound that has covalent bonds. So this is dry ice. Dry ice is just the solid form of carbon dioxide. But carbon dioxide in gas form sort of looks like that. This is carbon dioxide solid and gas. It looks exactly the same in both cases. The only difference is the individual molecules are closer here than they are over there. Each molecule, remember, is independent. We said with ionic compounds, each sodium doesn't have a specific chloride that goes with it. You have a collection of sodium ions, a collection of chloride ions, and they're in a 1-to-1 ratio. In a molecular compound, covalent bonds, we have individual molecules. Those two oxygens go with that one carbon. And until you have a chemical reaction to break them apart, they are one unit, called a molecule. So now, last week, maybe 2 weeks ago, we learned about the Lewis symbol. We just took the letters and put dots around them. Today, we have to talk about Lewis structures. These are the ones that I said might make you throw up a little bit in your mouth a couple weeks ago. So, Lewis structures are essentially drawings of molecular compounds with covalent bonds. We're going to draw them like this. There's going to be a stepwise set of rules that we'll go through. This is essentially what they look like. We're going to have the letters for the elements. So these are 5 different atoms. And then we're going to draw dots around them representing electrons. The most important thing to remember here is that everything has to have 8 electrons. We're only going to draw valence electrons. Valence electrons react. They're the ones that do things. The non-valence electrons will do absolutely nothing for us. So we're going to draw valence electrons, and noble gases have 8. Remember, we have 1, 2, 3, 4, 5, 6, 7, 8. Noble gases have 8 valence electrons, and everything makes a compound in order to get to that 8. So the fact that every element in our compound has to have 8 is called the octet rule. An octet is 8 electrons. If you draw a Lewis structure and you have an element or an atom that does not have 8 electrons, it is wrong. The octet rule is the rule. Every element, every atom is going to have 8 electrons. So we said the octet rule is that everyone has to have 8. And those 8 electrons are going to exist in 4 pairs. You are never going to have single electrons in a Lewis structure. They're always going to be in pairs. And so because everything has to have 8, and they come in pairs, everything is going to need 4 pairs. The only exception to the octet rule is hydrogen. Hydrogen can only have 2, and it has to have 2. Just like everything else has to have 8, hydrogen can only have 2. And that's because, if we look up here, hydrogen is in 1s, right? That 1s only has 2 arrows. When we were doing the orbital diagram, we said 1s2. And there is no 1p. So normally, that 8 valence electrons comes from the 2 s's and the 6 p's, which is 8. But hydrogen in the 1s doesn't have a p to go with it. So hydrogen can only have the 2 from the 1s. Then, once you get down here, now you have 2s and 2 p's, now you can have 8. So everything has to have 8, except hydrogen, which has 2. So, for our Lewis dot symbol, we just had dots around our one atom. It's essentially going to be the same, but when we make a structure, we need to count the total number of valence electrons that we have available to us in our compound. And so to do that, you just have to count how many valence electrons each individual atom has and add them up. So let's just review a little bit. How many valence electrons does hydrogen have? 1. Chlorine has 7. Oxygen 6. Nitrogen 5. Carbon 4. So if you can do that, you can find the total number of valence electrons that we'll need in a compound. And so, if we look at what this is asking, is how many bonds does each atom want to form? It's going to form one bond for every electron that it needs to gain. So hydrogen, you said, has 1. It needs 2. So it needs to gain 1, and so it's going to form 1 bond. Chlorine has 7, it needs 8. It only needs 1 more, so chlorine in our Lewis structures will only form 1 bond. Oxygen, nitrogen, and carbon each have 1 fewer electron to start than the one before it, so they will make 1 more bond. Carbon only has 4, so it needs 4 more, and so it's going to make 4 bonds. For every bond an atom makes, it's going to gain 1 electron. So these are our rules for making Lewis structures. I'm not going to read through them. We're going to work through examples. Okay? Lewis structures are like puzzles. They're not hard. You just have to work through them and get them done. And the more that you do, the better you'll get at it. The shortcuts you'll learn, you'll get through them quicker. Okay? So the first one we're going to make is a Lewis structure for formaldehyde. And we're given the formula CH2O. First thing you always want to do is find out how many valence electrons we have to work with. So how many valence electrons does carbon have?
4.
There's 4. How many does each hydrogen have?
1 each.
1 each. So we got 4 plus 2 is 6. How many does oxygen have?
6.
6. So we have 12 total. Does everybody see how we counted that there were 12 valence electrons in formaldehyde? Okay. So once you count that, I would suggest writing that number down. Just write it on your paper. Once you've got that, what we need to do is we need to write an atomic skeleton. It doesn't matter which order you do them in, they're completely separate from each other. So the atomic skeleton is going to be arranging the atoms in the correct shape, completely ignoring our electrons. Okay? So for the skeleton, formulas normally will be written in such a way to kind of tell you what that skeletal structure looks like. Normally the first element is going to be in the center. And then all of the other elements will be around it. The more you do, the better you'll get at making these skeletal structures. Hydrogen, oxygen, and halogens will never ever be in the center. Hydrogen, oxygen, and halogens have to be on the outside. There is no other option. There will only be a few different elements that you'll ever actually see in the middle. Most of them are these right in here. Carbon, nitrogen, oxygen, sulfur, phosphorus, silicon, maybe selenium. That's probably about all you'll ever see. So most of the time, one of those will be in the middle. But for the entire semester, if you're not comfortable figuring out what the skeletal structure is, you're always welcome to ask me. I am not testing you on being able to go from a formula to a skeletal structure. Okay? So in this case, carbon is in the middle, and then I have 2 hydrogens and an oxygen. It doesn't matter where I put them, but I have 4 sides, and so I put those 3 on 3 of the sides. And it doesn't matter where they go. I'm going to put hydrogen, hydrogen, oxygen, but you could have gone hydrogen, oxygen, hydrogen. It really does not matter at all. Okay? You just need 2 hydrogens on 2 different sides, and oxygen on a third, and the 4th one needs to be empty. So we go back to our steps. Step number 3 is put 2 electrons, which 2 electrons is 1 pair. That represents a single bond. Okay? That is a single covalent bond between every set of atoms that are bound together. Think of this as the glue that you have to have to hold your structure together. Okay? So I'm going to put 3 pairs like that. That holds this structure together. The rest of the electrons can go where they need to go, but if you get rid of any of those 3 pairs, the structure doesn't exist. If you get rid of that, that hydrogen is going to float away. So you can't get rid of that pair. You know you have to have those 3 pairs there. Step 4, it says add remaining electrons to the outer atoms to get them their octet. And so we have 12 to work with. We've used 6. So we have 6 more. So I'm going to come to this hydrogen, and I'm going to say, is that hydrogen happy? Does it have all the electrons that it needs?
Yes.
Yes. Remember, hydrogen is the exception. It only needs 2. So if it has 2, even though it's sharing, it claims both. Both the hydrogen and the carbon are going to claim both of those electrons. So then I come to that hydrogen and say, well, that hydrogen also has 2. So it's happy. Now I come over to the oxygen. It has 2. How many does it need?
6.
It needs 6 more for a total of 8. So I happen to have 6 extra electrons laying around to play with. And so I'm going to put the pairs, the 3 extra pairs, around that oxygen. I'll put 1 pair on each side, just like we did with our Lewis symbol. So now that oxygen has 8. Now I step back. I'm out of electrons. I can't put any more anywhere. But I have to decide, do I need to move any electrons around? So we said the hydrogen each have 2. They're happy. Oxygen has 8. It's happy. Is carbon happy?
No.
No, it's not. It only has 6, and carbon has to have 8. So we come to our last step, number 5 here. It says, if we need to move electrons so that everything gets its octet, we can do that. And we take unshared electrons from outside atoms, so these are unshared pairs, and we move them in towards the center. So you can take any of these 3 pairs. I'm just going to pick this one. I'm going to move it into here. And when I do that, I get that. And so instead of having a pair here and a pair there, I have 2 pairs there and nothing on the bottom. This is called a double bond. So that's a single bond. That's a double bond because there's 2 pairs. So now if we count, each hydrogen has 2. Oxygen still has 8. Each hydrogen has 2. Oxygen still has 8. Even though it's sharing 4 of them, it still counts all 4. Oxygen has 8, and carbon has 8. So based on the octet rule, everything is happy. The last thing you can do to check is the number of bonds we said each element wants to form. Hydrogen, we said, has 1, needs 2, so it needs to gain 1, so it should form 1 bond. Each hydrogen forms a single bond. Oxygen, we said, had 6 valence electrons. It needs 8, so it's going to want to gain 2, and it does that by making 2 bonds. And you can make 2 bonds either as 2 single bonds or 1 double bond. So here, oxygen has made 1 double bond. So it's behaving like we would expect it to behave. Carbon has 4 valence electrons, so we expect it to make 4 more bonds to get the last 4 that it needs. And it made 2 single bonds and a double bond. That's 8 bonds, so carbon is happy. Everything is happy. We've made our structure for formaldehyde. You don't need to draw the circles. I just draw those so that you can see which electrons go with which atom. Yeah?
So the same thing as the dash? The dash?
Yes. And so some of you who have done this before might like to draw dashes like that. That is correct. I will never mark that wrong. and some of the other professors here would actually prefer that you do that. To me, this is more confusing than this though. Because here, you just count how many dots does each one have. Over here, you have to remember that each line is 2 dots. And so oxygen doesn't have 8 dots around it. It has 4 dots in 2 lines. And so to me, this is harder to visualize than octet. It's easier to visualize bonds because sticks look more like bonds. They're holding them together. But this, to me, is easier to visualize the electrons. So whichever one you're more comfortable with, you're welcome to use. I am going to use the dots. And that's what's up on our slides. So this is the step-by-step instructions on how to do what we just did. Now we're going to do hydrogen cyanide, HCN. First thing we have to do is figure out how many valence electrons we have to work with. Hydrogen has 1. Carbon has 4. We're at 5 total. Nitrogen has 5. So we have 10. So I'm going to write 10 down. And this is one of those examples where the formula is written just like the skeletal structure needs to be written. So I'm going to put HCN. Carbon is in the middle. So once we count our electrons, we make our skeletal structure. What was the first thing we did with our dots?
We put them around.
We made single bonds to hold everything together. So that's our first 4 electrons. Now we've held everything together. What was the next step? Make everything happy on the outside first. Is hydrogen happy?
Yes.
Yes. Is nitrogen happy?
No.
No. How many more does it need? It needs 6 more. So I'll give it 6, but now we've used 2, 4, 6, 8, 10. We only have 10. So hopefully everything's happy, otherwise we're going to have to move things. Hydrogen's happy, nitrogen's happy, is carbon happy?
No.
No, it's not. It only has 4 electrons. It needs 8. So it's going to have to make more bonds. I can't move anything from this side. There's nothing more on the hydrogen to move over. And so I'm going to have to take some of these nitrogen electrons and share them with carbon. So let me take those. Now I've got that. Is that the correct answer?
No.
No. Carbon now has 6. So now I'm going to take these, move them over. I've now made a triple bond. There are single, double, and triple bonds. There are no quadruple bonds. Hydrogen's happy. Carbon has 8. Nitrogen has 8. Hydrogen made 1 bond like it wants. Carbon made 4 bonds, a single and a triple. Nitrogen made 3 bonds. Nitrogen likes to make 3 bonds. So everything is happy and it can go on its merry way. Yes?
I thought we always put the first letter in the middle.
A lot of times it is, but not always. And so in this case, the first letter is H, and H's, like I said, are never in the middle. And so then I would go, well, it's not that one, what's the next one?
Okay.
But you can always ask me, and I would certainly tell you HCN. Again, step by step on what we did. Now we're going to do some more. So we've got CO2. How many valence electrons do we have in CO2?
16?
16. So carbon has 4. Each oxygen has 6. So 6 plus 6 is 12. Plus 4 is 16. So CO2, we've got carbon in the middle. I'm going to do 2 oxygens like that. You could do oxygen, oxygen. Doesn't, yeah, go ahead.
Since we know that carbon needs 4 bonds, can we go ahead and put the 4 bonds in the middle?
No. There will be, you don't necessarily know if it's going to be double-double or single-triple.
Okay.
Because that could be either one. In this case, it's a little more obvious, but some compounds it will be not as obvious. I think this one might be one of them, the SO2. So we've got 16. I'll put my glue in. That's 4. Then I'll put the rest of them on the outside. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now I'm out. Oxygens are happy, carbon is not. So I'm going to have to move electrons in. Now we come across the question, what do we do with them? Because I can move that one to there. That gets carbon 6. I can move that one to there also and do a single and a triple. Or I can move 1 pair from each side and do a double and a double. Let's write both of them out and figure out which one we think is correct. So we've got the 2 here. Which one is the correct one?
The bottom one.
Why the bottom?
Oxygen share.
So you're both correct. It's balanced because they want to have the correct number of bonds. Oxygen only wants to make 2 bonds. Carbon wants to make 4, so carbon is happy with either of them. But oxygen only likes to make 2 bonds. So here, the oxygen has 3, that oxygen has 1, neither of them are happy. Down here, they both made 2. Now, those of you that have done this before, how many learned about resonance structures? No. Good. Okay, that makes it more complicated and we're not touching them. Okay? What resonance structures is essentially, it says in real life, both of these exist, and the real structure is somewhere in between them. So we're not doing that. For us, there's a right one and a wrong one. So carbon dioxide is the bottom one here. Carbon with 2 double bonded oxygens. Now let's do sulfur. How many valence electrons are in the sulfur dioxide?
18.
So we have, there's 6 in sulfur, 6 in oxygen, so 6 times 3 is 18. So again, oxygen is always on the outside, so we'll do SO2. I'll put my first 4 in. Again, I'll just got 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oxygens are happy. I've still got 2 more electrons left. Only place I can put them is on my sulfur. Fill the outside, if you have any left, then start filling the inside. Is this the final structure? No, why not? Sulfur doesn't have 8. Sulfur only has 6. So, what do you want to do? We need to get sulfur to 8. Let's move a pair. Just pick one. So let me move that there. That's what we've got now. Is that the final answer? How many electrons does oxygen have? 8. How many does sulfur have? 8. How many does oxygen have? 8. How many bonds did oxygen make here? 2. How many did sulfur make? 3. Sulfur only wants to make 2. How many did oxygen make? 1. Oxygen wants to make 2. But in this case, there is no way to get around this. Because we can't take one from each. That's not going to work. And we can't move another pair here because then sulfur would have 10. So this is actually the best structure we can make for SO2. The octet rule is the most important rule. Number of bonds things like to make is a secondary rule. Get the octet rule and then try to make things happy in terms of bonds. If you can't do it without breaking the octet rule, then leave it be. So in this case, it would seem like it would be symmetrical. I mean, you have an S and 2 oxygens. The 2 oxygens would either be single bonded each or double bonded each. But in actuality, we have a double bond and a single bond. Everybody get that one? Okay. So now let's go on to a little bit more, not more complicated, it's bigger. So, the structures that we did, in majority of the compounds that you will do will have 1 center atom and then up to 4 atoms going around it. Okay? The exceptions to that I will ask you to know how to do are these 3. C2H6, C2H4, C2H2. It works the same way, but instead of having 1 center atom and then 4 around it, we're actually going to have 2 center atoms. So in this case, we said hydrogens can never be in the center. Carbons are pretty much always in the center. So what this is going to look like is we're going to have carbon, carbon, and then 3 hydrogens on each. We need to count how many valence electrons we have to work with. Carbon, each has 4, so that's 8. Each hydrogen has 1, so that's 6. 8 plus 6 is 14. So I have 14 to work with. First thing I need to do is put in my glue, which is going to be a lot. We'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And I'm out. Hopefully, I'm correct, because there's not much I can do if I'm not. Are all the hydrogens happy? Every single one of them?
Yes.
Yes. Are both carbons happy?
Yes.
Yes. Each carbon has 4. Each carbon has 4 bonds. So this is C2H4. Sorry, that's C2H6. Now let's go on to C2H4. How many valence electrons does C2H4 have? We lost 2 hydrogens.
12.
So we're going to lose the 2 electrons that came with those 2 hydrogens. So now we have 12. I lost 2 hydrogens, so let me erase these 2 hydrogens. When I did that, I erased 2 electrons. Sorry, I erased 4 electrons with my 2 hydrogens. But I only actually lost 2. Which means I have 12, but I've only drawn 10 so far. That means I have 2 electrons that I can play with. So I need to find the perfect spot to put them to make everything work.
The double bond in between the middle.
Correct. If I put them there and make a double bond between the carbons, everything is happy. Now, let's do C2H2. We're going to lose 2 more hydrogens. We lose 2 more electrons. So I erase all that, and again, I have 2 electrons that I need to put somewhere. Where can I put them?
You kept the one in the middle. Did you mean to do
That?
that? Yeah.
Yes.
Okay.
Make a triple bond in the middle.
Make a triple bond. So now, hydrogens have 2. Carbon has 8. Carbon has 8. Hydrogen has 2. And everything's happy. So these 3 are the 3 that I expect you to be able to do with multiple center atoms. If there's one center atom, I can ask you any compound known to man. Okay? Really, none are more difficult than the others. Count how many valence electrons you need. Put your glue in, feel the outside, feel the inside, move electrons in as you need to. Everybody comfortable doing this? Okay. So this is the last slide we're going to go over tonight, and then we're going to pick up on Thursday. Okay? Do not miss Thursday. What we have to do in lecture next Thursday is a sort of complicated thing that you will have to do on quizzes, on exams, very likely the final exam. Okay? It's an important thing. Try not to miss Thursday along with lab. What we're going to be talking about is the shape of these molecules. So what we're drawing up here is in 2 dimensions. But molecules exist in a 3-dimensional world. And so we have these bonds, but those bonds can stick multiple different directions. And the shape of the molecule makes a huge, huge difference. Okay? For example, taste. So this is, I believe, glucose. And so that is what glucose looks like. What does glucose taste like? It's sugar. I mean, glucose is, table sugar is sucrose, essentially 2 of these stuck together. Glucose is the most basic sugar around. And so what your taste buds do is they have essentially a lock shape that if something comes along that is shaped like sugar, it'll fit into that lock. And if something fits into that lock, your brain senses it as sweet. So artificial sweeteners, like NutraSweet, look absolutely nothing at all like sugar. They are not sugars at all. But they have a little piece of the molecule that looks like the most important part on glucose. So they still fit into that key, which makes your brain taste sweet. Same thing with smell. Okay? Also, enzymes in our body. Okay? Enzymes in our body they're proteins. Everything in your body that does something, that has a function, is a protein. It's an enzyme. And the bonds in those enzymes are just thousands of atoms bonded together to one giant molecule. And one bond being this way versus that way, I mean, it's about a 40-degree difference, can make the difference between an enzyme working or not working. One bond that way to that way in a drug that you're taking, a therapeutic drug that you're taking, can make the difference between it working and not working at all. In terms of the smell, I worked for a few years at a chemical company, and what I did is I made cosmetic emulsions. So emulsions are oils in water. I essentially made sunscreen and skin lotions and makeup and things like that. And we worked with it was Dow Chemical, which is literally the biggest chemical company in the world. And I worked with customers from all over the world. And so sometimes we would get weird requests from companies that wouldn't make sense to us, but in their culture, it made sense. And so I was working with, it was a laundry detergent, and I got a request from a company, not in the US, that said, we want our laundry detergent to be scented with the scent molecule called limonene. Now, I was an undergraduate in college. I had no idea what I was doing other than how I was doing it. My boss was actually a theoretical physicist whose position had got eliminated, and they moved him to selling sunscreen. He had no idea what was going on, and so we both looked at each other and said, they want limonene. I'll go online, order some limonene, put it into their laundry detergent. What can go wrong? I ordered the stuff, it came in, I opened it, and it smelled like a wet dog. And I went to my boss, and I said, take a whiff of that. And because he was a theoretical physicist, not a chemist, he stuck his nose in it. He didn't waft. He stuck his nose in it. And he said, well, he was British, and so he goes, bloody hell, that smells like a wet dog. And I said, I know, doesn't it? And I said, what are they thinking? Why do they want their clothes to smell like this? And we decided, well, it's a different culture. Maybe they want their clothes to smell like this. And so we go with it. We smell out the entire building with this stuff when I make it. Everybody's complaining about it. I send it off. A week later, he gets an email from them saying, what did you put in this stuff? It smells like a wet dog. And we said, we put in what you wanted us to put in there. We thought you wanted it like that. We said, no, we don't want to smell it like this. What did you put in here? We said, it was limonene. You asked us to put limonene in there. And they said, well, did you put D-limonene or L-limonene? And we looked at each other and said, what's the difference? The difference is what direction that bond points. If the bond points one way, it smells like a wet dog. If it points the other way, it actually does smell nice. And so I went back online, figured out, okay, I was being cheap. I ordered the cheaper one. I didn't know what the difference was. Ordered the cheap one, right? Ordered the more expensive one, and it smells nice. So the shape of a molecule makes a huge, huge difference. And that's what we're going to be learning next week. And so, coming back to the taste, you know Splenda, right? Splenda is now now it's stevia, but Splenda for a while was the big new artificial sweetener. And do you remember the motto of Splenda? What's their tagline? Made from sugar so it tastes like sugar. What Splenda is it is essentially sucrose. They start with sucrose, and they replace these oxygens with chlorines. And a chlorine is essentially the same shape and size as an oxygen and a hydrogen combined. And so to your body, it fits in the same taste bud. It tastes sweet, but these oxygens and hydrogens are what give it the energy. So you take those hydrogens off, it tastes sweet, but your body can't break it down, it can't get any energy out of it, and so it just passes through your body and it has no calories. And so what we're going to do on Thursday is we're going to learn how to take the Lewis structure and turn it into a three-dimensional structure. So we'll do it on paper, on the board. We'll learn how to draw it, and then in lab, the actual lab portion is you'll have a kit with balls and sticks and stuff that you'll actually make three-dimensional molecules. So remember to bring your notes on Thursday. Don't just bring your lab, bring your notes.